Okay, hi. So we're continuing our discussion of integral domains and ideals and rings and related topics. And so last time we talked about maximal ideals, and that was an ideal for which the quotient ring was a field. And then I defined an integral domain so that I'm not showing that page now because it's the previous page, but in fact you can kind of see the definition here in this comment. So it means that an integral domain is a ring in which, commutative ring, in which if you have a times b is 0, then either a is 0 or b is 0. So the usual kind of cancellation. So a typical example would be z. It's not a field, it doesn't have division, but it has this weaker property, you know, that if you can't multiply two non-zero things and get 0. And then I said an ideal is prime if the quotient is an integral domain. By the way, I should probably give a non-example. So, you know, most of you are probably used to rings that are integral domains. Those are kind of normal rings that you would have encountered before in life. So, what's a counterexample? So let me actually note that there are plenty of non-examples. So kind of, it was long believed in math that these are more or less the only interesting rings. That's now known to be false, and there are important things, for instance, in algebra and algebraic geometry that you need, where you need rings which are not integral domains. They play an important role in lots of areas of math. But it's natural to believe that the only interesting rings are integral domains, right? Because they include Z and fields and polynomial rings and all the rings you're used to. So let me just note what do the non-examples look like. So for instance, you can form, so let F be a field. You can form f of x, f adjoin x, the polynomial ring over f. Okay, that's a perfectly good integral domain. And then you can take the quotient, you let I be the ideal generated by x squared equals the ideal, which consists of p of x such that p of x equals x squared times f of x. Right, so it's the set of all polynomials which are divisible by x squared. So you can easily see that's an ideal. It's things that are the form x squared times something, clearly closed under addition and multiplication. And then you can form the ring f of x mod I. And now this ring, what does it look like? X squared has been set equal to 0, but x has not. So this looks like f plus f times x bar. So here, like I did yesterday, I'm using x bar to denote the image of x inside this quotient set, so the coset of x. So this looks like elements of the field plus elements of the field times x bar, and x bar squared is now 0. So it's like the field plus another little kind of infinitesimal piece, and that piece satisfies when you square anything in it, you get 0. But x bar is not 0, right? We didn't quotient out by x, right? This is the ideal generated by x squared. That's the key point. If I took it in the ideal generated by x, then you'd say, well, x bar is already 0, so nothing happened. But in this case, I quotiented out by x squared, but not x itself. So there's this element x bar which is not 0, but it times itself is 0. Okay, so that's a classic example of a ring which is not a domain. And rings like this, actually, they seem like weird. You know, when I first encountered them, I thought, well, right, whatever. They seem kind of like weird mathy constructions, but actually, it turns out they're meaningful and interesting. I'll just, without derailing the course to get into why, I'll just say that they are they contain a lot of surprising and cool information. All right, so I wanted to at least mention that there are plenty of interesting rings that are not integral domains. All right. But now I want to return for a minute to theory of integral domains and prime ideals. So let me say a few things about this theory, which is very complementary to maximal ideals and is very powerful and interesting in its own right. So let's talk a little bit about these prime ideals. So I defined it last time. So I'll just recall I in R is prime if R mod I is an integral domain. Okay, right. So what does it mean to be prime? let me show that this definition can be restated in kind of a neat way. So lemma I is prime if and only if the following holds: whenever AB in I, then either A and I or B and I, or both. That's kind of subsumed in the meaning of or, but I should say it explicitly. Okay, so whenever you take a product of elements and they land in the ring, in the ideal, then either the first one was in the ideal or the second one was in the ideal. Okay, the proof, this is actually just a restatement of the definition in direct terms, right? So the point is that R mod I is a domain. That's if and only if whenever equivalence class of A times equivalence class of B equals 0 in R mod I, then either equivalence class of A is 0 or equivalence class of B is 0 in R mod I. Right? But what does that mean if you unpack it? It just means that whenever AB, right, now take any AB in the ring, right, whenever AB in I, then either A in I or B in I. Okay, right, I mean, what does it mean for the equivalence class to be 0? It means that you're in the subgroup or the ideal that you quotiented out by. Right, so this lemma is almost contentless, but it's worth saying it because now we see why prime ideals are called prime. So let's give a quick lemma here. Lemma. So what is it? Maybe lemma isn't even the right word. Let's say example. Let nz equal I in z be an ideal. So I is prime. A prime ideal if and only if n is prime. Right? A prime ideal is just one that's generated in the integers by a prime number. And we'll see in a little bit that the same thing is true in a polynomial, right? Okay, so what's the proof of the example? So the proof is, so let A and B be in Z. So AB is in I. That's if and only if AB is in NZ. And that's if and only if N divides AB. Right? So what does it mean? So I is prime if and only if whenever N divides AB, either N divides A or N divides B. And that, as we know from chapter 2, is an equivalent condition to being a prime number, right? So, okay, so I prime if and only if N divides AB implies either N divides A or N divides B. And this, in turn, is if and only if N is a prime number. Right, that was enough to characterize. So by our basic work with primes, with our basic definitions with LCMs and GCDs and the basic arithmetic, we saw that condition was equivalent to a number being prime whenever you divide AB. Either you divide A or you divide B. It's not exactly the definition of prime we gave, but a little thought and a little work with GCDs showed that was equivalent, right? But now, translating that into the ideal world, that exactly says that I is a prime ideal. Okay? So it really is a generalization of prime number in the usual sense. Incidentally, the same thing is true in a polynomial, and as I mentioned before, we'll discuss that in a few minutes. Okay, so that's the deal with or at least some basic deal with prime ideals. Yeah, so this is quite good. Yeah, so the book also emphasizes this. The book also emphasizes. Oh yeah, all right. Let me give a. No. I'll stop there. The book also emphasizes this construction of quotient rings, or they call them fields of fractions, which is a good notation, so I'll stick with that. So it's not a quotient ring or quotient field, it's a fraction field. So let me give a word or two, say a word or two about that. Oh, yeah, sorry. This lemma is not quite correctly stated. That's why I was hemming and hawing a bit. N is prime or... okay, great. So let me do a slight revision before I move on. I said I is prime infinitely if n is prime. The answer is that's infinitely if n is prime or n is 0. Right? Because in fact, proof is exactly the same. So I'll just add it on. Because in fact, if you think about it, 0 divides AB implies either 0 divides A or 0 divides B. What does that mean? That means that AB is 0 implies either A is 0 or B is 0. But that just says that Z is an integral domain. So, in fact, so it's not quite true that the prime ideals are the same as the prime numbers. There's one additional one, which is the 0 ideal. So there's a little bit of a difference between the ideal theory and the arithmetic there, and that because Z itself is an integral domain. So if I quotient out by 0, I get that itself. Okay. If n is a prime number, then these ideals are also maximal, right? Any maximal ideal is prime. It's clear because any field is an integral domain, but any prime ideal isn't necessarily maximal because in this case you have prime ideals which are numbers which correspond to prime numbers, but you also have a prime ideal 0, which is not a maximal ideal. So the concept of prime ideal and maximal ideal are also a little bit different from each other. Okay, good. So that's all worth storing away. We won't do much with it, but it's just good to know. Okay, finally, let me talk about this field of fractions construction. So, field of fractions. Okay, so what is that? It's a way of constructing out of an integral domain a field. So, I'm just going to state it kind of as a theorem, and then I'll just kind of say what the construction is. In fact, the most interesting way is to characterize it, which the book does very nicely. So let R be a domain, an integral domain. So the field of fractions is the smallest field that R embeds into. Okay, so let me say what that is. So I'm gonna write out what that means, and then I'll explain how to construct it. So Q of R, the field of fractions of R, is a field so that R contains in Q of R, and if R contained in F, so R is contained in Q of R, and if, I'll be more precise, R to F is a one-to-one map from R to a field. So suppose that you have another one-to-one map from R to F, then I'll draw it this way. Then there exists a unique map from Q of R to F, making the diagram commute, right? So whose restriction to R is the original map. Let's give it a name. Let's call it phi. So there's a unique map. Let's call this psi from Q of R to F, whose restriction to R is phi. So psi restricted to R is equal to phi in simples. It's probably easiest to write it this way. So it produces, so whatever this is, you get a map out of it into that field for free. Okay, so that's how you should think about the field of fractions. It's the smallest field that R lives in, right? If you ever have another field and you can put R into it in a one-to-one way, then you can put the field of fractions into that same field. Okay, so that's kind of an airy-fairy way to think about it. What's the concrete way? So concretely, Q of R is a set of fractions. So Q of R is the set A over B. Well, okay, I'll say it this way. Is the set A comma B such that AB is an R, B is not equal 0. Quotient out by an equivalence relation. And what's the equivalence relation? A comma B tilde A prime comma B prime if and only if what? So this is supposed to be A over B, and this is supposed to be A prime over B prime. So that's AB prime equals BA prime. Okay? So in other words, right, if you think about this equation for a minute, that's saying A over B is A prime over B prime. So, in other words, so you formally make a field, right, by making fractions out of elements of R. So for any pair of elements of R, you make their fraction, this A comma B, but then the point is sometimes two fractions are equal, right? This is, as you know from your elementary school arithmetic, right? If I take two fractions of integers, sometimes their ratios happen to be the same. And when does that happen? If and only if this cross ratio condition is satisfied. So I make this a tilde, and then this, you can, you have to put an addition on this and multiplication, right? So how do I define AB plus A1 B1? I define it by addition of fractions, right? So in other words, I make this B1B and I make that BB1. Steph, I think Asher's awake. So, right, so I take this thing and I multiply top and bottom by B1. So that's going to be AB1. And I take this thing and multiply by top and bottom by B. And that's A1B. And then that's BB1. Okay? And then how do I define multiplication? AB, A1, B1. That one's the obvious way. A1, BB1. Okay. So I will, in no way will I check that this is a ring for you. You guys can easily do it. So these extend to ring operations, and then this whole thing makes what you have to check. I mean, of course, you have to check that these things are operations after you pass to the quotient. So there's something to check. Like I said, I leave it as an exercise. The book leaves it as an exercise too. It's a rare math book that writes out this proof, I think, just because it's a good thing to check on your own. And I'll stick with that tradition and not check it. But it is certainly true. And you can check easily also that it satisfies this condition, right? Because what's the point? The point is that this thing is made just out of quotients of elements of R. So if I have a map from R into a field, and then I take a pair A comma B, I can always map it to phi of A over phi of B, right? It always it always extends to QR in the obvious way. Okay. So that's a nice thing to think about. So that's a nice construction. So you could always go from a ring, an integral domain, to a field. So the lesson is kind of fields are everywhere. Yeah. Okay. And the example, in case it's not clear from the construction, is that if you do it with Z, you get the usual rational numbers. All right. Great. All right. So that's a quick tour of prime ideals and that stuff, and we'll do some exercises in those. All right. So yeah. So maybe it's okay. So this kind of almost finishes this second to last lecture, and we have kind of one more. So the kind of last thing I really want to talk about is this notion of a unique factorization domain. So I want to start. Maybe I'll say a few words about it in this lecture, and then I'll spill the rest over. Yeah, I mean, I'm going to start with the Euclidean domains, and then, yeah, okay. So we'll start with Euclidean domains in the rest of this lecture, and then we'll spill the rest over to the last lecture. Okay, so all right, so maybe that'll be a new page. I have 5 or 6 more minutes here in this lecture, and then we have one more lecture to follow later today. All right, some of these pages have writing on them. So, okay. All right, Euclidean domain. All right. So, these are a very special kind of integral domain that generalize the integers. Steph, are you there?
Yeah.
I think he's up.
Okay.
So these are integral domains in which you have a nice theory of factorization, as the book says. The main examples are integers and polynomial rings, but actually that's a little bit of a lie. There's also what are called rings of integers in number fields, and they provide very interesting examples. So let me give a definition. So let R a domain, an integral domain. So the idea is that you're supposed to have a function on this domain called the degree function. So a degree function is a function d, and it goes from r minus 0, and it lands you in the natural numbers. Yeah, so they say natural numbers union 0. That's right, because you can certainly have degree 0. Degree 0 polynomial makes sense. Natural numbers union 0, also known as z greater than or equal 0, however you want to denote that. So you have this degree function, and the property is that the degree of f times g, right? So thinking of it in terms of a polynomial, it's supposed to be degree of f plus degree of g, but in fact that you can demand a little bit weaker than that. You can simply demand that it be greater than or equal to the max of d of f, d of g. We'll see the reason for that. We'll see the reason for that in a minute. So remember, it's not literally a degree function, so you should think of it like a degree of a polynomial, but it, there's a little bit more to it than that. It's not always literally that. But we'll start with that as our kind of motivating example. And of course, there's a Euclidean algorithm. So for f and g in r minus 0, so I guess he's just demanding that they're both non-zero. That's fine. There exists qr in r such that you can divide g by f with remainder r. So f is qg plus r, and degree of r is less than degree of g. Right? So this is exactly the Euclidean algorithm that this exactly Euclidean division that we discussed in the integers, right? This exact kind of form of it, which is that you can take one and divide it by the other, and the remainder has a smaller size. Right? So we use that over and over again in our basic theory of the integers, and now the point is that in other more general situations, the same kind of thing holds. So the examples. So before we get into the theory here, what are the two examples? The two main examples. The one that we discussed already earlier in the class is r is z, and then d of n is absolute value of n. Okay. So this is why you need d of fg is greater than or equal max d of f d of g, because you can. It's not always. It's right. It's not exactly the case that it's the sum of f and g as it would be for the degree of polynomials. Right. In this case, it's more like the product. But at any rate, it's always the case that the product is bigger than or equal to the maximum of the two of them. So this first axiom is automatically satisfied, and the second axiom is just division in the integers. Yes, we proved the heck out of that, right? And so finally, I'll finish this lecture by talking about why it works in polynomials. So suppose R is f adjoin x, and here f is a field. Then we claim that it also works here. So d of f is the degree of f. Okay, so there's no absolute value, just the degree of a polynomial, the largest non-zero term, right? And in this case, we have d of fg is d of f plus d of g. So it's actually a little different than the integer case, right? When I multiply two polynomials together, I add the degrees. And so it certainly satisfies this axiom. That's clearly true. Okay, and now why is the second thing satisfied? Let me spend a few words on it before we go today. So essentially, the answer is that you have this this thing is polynomial long division, right? So how do you justify this? it's sort of a good exercise to work out, but I'll kind of sketch out how it goes. So the idea is that you kind of it's very similar in a lot of ways to the integer case. So you have two polynomials f and g. So the point is you want to try to divide g into f. So if degree of g is greater than degree of f, so division, let's talk about that. So case 1, if degree of g is greater than degree of f, you set q as 0, right? We want f as qg plus r. In that case, you set q as 0 and r as f. And that works, right? It plainly works. All right, so what if the degree of g, so let's kind of go down to see how it's going to work. What if degree of g is equal to degree of f? If d of g equals d of f, what's happening there, right? So how do we prove this? So you want to divide g into f, and you want to get a remainder which has strictly lesser degree than d, which is degree of f, which is degree of g. Okay, so the point is, if they have equal degree, then g is an x to the n plus dot dot dot, and f is bn x to the n plus dot dot dot. I guess I'm implicitly calling the degree n here. And so then the point is, we set in this case q, so I'm going to multiply q by g to get f. So we set q is equal to bn over an, which has degree 0. And of course, these are both non-zero elements of a field, and because it's a field, I can divide. So notice how I use that axiom there. I demanded that I'm working over f of x. Where is it? F of x where f is a field, not where f is an arbitrary ring. That's because I needed to divide. And it's exactly in this step I needed to divide. And then f minus qg, so f minus qg is a polynomial of degree less than n, equals r is a poly of degree strictly less than n, right? Because I've set it up to cancel out the terms of degree n, and these guys are equal. So that's how I get f equals qg plus r in this case. And if degree of g is less than degree of f, it's extremely similar, right? So let's take a look. If degree of g is less than degree of f, so remember, I want to write f equals qg plus r. So in other words, I do exactly the same kind of thing. I try to divide g into f, and the point is that degree of r has to be less than degree of g. So in the previous example, degree of g and degree of f were the same, and so I just had to be less than that same n. Okay. So how do you do it more generally? So the point is that you build this q to make f and g equal in all of the degrees up to the degree of g. So we'll do similar. So we'll write f is all right, I'll stick with the same notation. Bn x to the n, bn minus 1 x to the n minus 1 plus dot 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 plus, let's call it bm x to the m. Okay, 1 minute, bud. And then we're going to write g is a m x to the m plus lower order terms. And now the sort of thing to show is that you can write, the point is you design q such that q times g, so we make q times g equal to bn x to the n plus bn minus 1 x to the n minus 1 plus bm x to the m plus something, right? And the point is that in the fact that you can do that is just an easy inductive exercise on m and n, right? So the point is the linear term, the zero order term, is just going to be bm over am, right? And then, sorry, not the linear term, zero term. And then the linear order term is bm plus 1 over am. You multiply by that and you get this notation. And so you just go up by induction and you see that there's some polynomial that you can multiply by it to equal out to these terms. And then you add all the lower order, and then the lower order stuff is r, whose degree is strictly less than G. Okay, so I'll stop there. And then next time we'll talk a little bit about this theory, and that video will be up almost the same time as this one. So thanks, guys. See you soon.